Okay, sorry. So first I'll go over what is a polymer. So a polymer would be made from monomers. So in this slide, you can see like an example of one of these monomers could be the molecule ethylene, which would go through polymerization and form polyethylene, which is one of the most common polymers. It's found all over the place. And then we also have different types of polymers. So there's linear polymers, which are made up of repeating monomer units. And note that linear polymers are not actually straight because there's tetrahedral geometry around the carbons. So I just thought that was an important thing to note. Then we also have branched polymers where linear chains branch off, cross-linked polymers where the polymer chains are connected to one another, and then network polymers, which have a 3D cross-linking structure. So they're, as you can see, they're the most cross-linked and connected to each other. And so then there's some different categories that all these different polymers can go into. So thermoplastics would cover generally linear and branched polymers, and these can be melted and reshaped. They can also be crystalline or amorphous. And thermoplastics are generally sort of what you would think of as plastics. So like your plastic water bottle, plastic bags, those kind of things are all thermoplastics. Then we're going to have elastomers, which are generally made up of lightly cross-linked polymers. They are viscoelastic. They have weak intermolecular forces, and they're very ductile. And some examples of these would be tires on your car, maybe your shoe soles, and other materials similar to that. And then finally, we have thermosets, which are generally made up of network polymers. They have rigid structures, and they change chemically during their setting, so they can't be melted and reshaped. So as you can see in this image, the thermoplastics aren't really cross-linked. The elastomers are a little bit more cross-linked. And then these thermosets are very heavily cross-linked, so that's giving them that rigid structure. And so an example of this would be sort of like these rigid buttons, which are made of bakelite usually. And also epoxies are also thermosets. Okay, so now we'll get into a little bit more about polymer-derived ceramics. So these are generally made through controlled thermal decomposition or pyrolysis of organosilicon polymers. And these are also, it's important to note that these are covalent ceramics. And so these can be made from many of these different pre-ceramic polymers that I have given this image of. So they're generally made from these elements: silicon, oxygen, carbon, nitrogen, and boron, or any sort of combination of those. And many of these pre-ceramic polymers that I've shown can be synthesized from chlorosilane, which is actually a byproduct of the silicone industry. So I thought that was pretty interesting. And then some advantages of polymer-derived ceramics are that they can be shaped, which allows them to have complex structures. So in my case, I've been spinning fibers, but you can also mold them and do many other things with the shape. You can also modify the molecular structure through reactions. They have low synthesis temperatures, around 1,000 degrees Celsius versus 2,000 degrees Celsius for a traditionally made ceramic. So that also leads to the lower energy consumption, which is definitely a positive. And then I'll go into a little bit about preparing PDCs. So the first step would be shaping them. So you could make fibers or other complex structures. Next would be cross-linking, which allows the 3D networks to form. And then finally, pyrolysis, which changes the pre-ceramics into amorphous ceramics and eliminates those organic groups. So you're left with an inorganic ceramic material. And then we have some applications of polymer-derived ceramics, which would be for lithium-ion battery anodes. There are some biomedical applications, such as drug delivery and bone tissue engineering. You can also create fiber-reinforced composites and different coatings to protect metal surfaces in extreme conditions. And I'm just going to quickly point to the jet engine, and that would be, you could make a ceramic matrix composite material, which could go inside here to improve the efficiency of this engine, because ceramics can reach such high temperatures. So that's, I think, a really important application of polymer-derived ceramics. And then finally, I'll give a little preview of what I'm going to be going over next week. So this sort of relates back to the little preparing slides that I showed you about preparing polymer-derived ceramics. So this is what I've been working on. I first shaped my pre-ceramic polymer. I used a polysilazane. So I spun fibers from this by mixing it with a spinning agent, and then I cross-linked this, and then I pyrolyzed it to create the ceramic fibers. So that's what I've been working on, and I'll talk a little bit more about that next week. And that's all I have for today. So let me know if anyone has any questions.
Oh, thank you very much for this very nice presentation.